forgotten to record it. I think it is recording now. Yes, it is recording. Okay. So, can you see the whiteboard? Hello?
Oh,
Yes, can you see the whiteboard? Ah, no, you
no.
can't. Yes, it is back now, I presume. Okay. So, we know that blockchains is a proper subset, a large subset, but nevertheless a proper subset of distributed ledger technologies. And we have discussed several of them, several generations of distributed ledger technologies. So generation one was obviously the Bitcoin. Bitcoin not as a cryptocurrency, but Bitcoin as a blockchain. Generation two was Ethereum. Generation three, a large number of general purpose distributed ledger technologies. And in particular, we considered Hyperledger family, but by no means it is unique. So there are many implementations of generation 3. And what is generation 4? Do you remember? Any idea what is generation 4?
Maybe some ledgers that are implemented on top of some other crypto, for example, Ethereum network.
No, everything on top of Ethereum is generation 2. You know, generation 4. Rim, are you with us?
Yes.
You know what generation 4 is, right?
Formula verified
Of
blockchain.
course. Generation 4 is our inner chain. A formally verified distributed ledger technology. Maybe a precursor to generation 4 was Tezos, which also contained some formally verified elements. But a complete formally verified stack is only our inner chain, which is being developed here at Innopolis University. And we're very happy to participate in this kind of development. So what are the main differences between the generations? Generation 1, Bitcoin, was actually to support only financial transactions. So this is for BTC cryptocurrency only. CCY is abbreviation for currency. And it has very rudimentary, we have seen there is some, but very rudimentary smart contracts capabilities, next to nothing. Do you remember from our lectures in that semester? So, what are smart contracts in Bitcoin? They do exist, but they are not really smart. Any idea?
Some
There
non-Turing
was
complete scripts.
What?
Non-Turing complete scripts based on
Indeed,
stack machine.
indeed. You're absolutely
basic based on prefix stack machines, something like that.
right. Postfix.
Postfix.
Non-Turing complete postfix stack machine, which is typically used for addressing transactions. So basically, this script, when you create a transaction, you specify the output, if you remember. The output designates the party which is entitled to use this transaction as a subsequent input if they verify themselves. So this language basically allows us to implement locking and unlocking, in particular unlocking mechanisms, so that the legitimate recipient of the transaction, who is in possession of the corresponding private key, can unlock the output of a transaction and use this output as an input of their subsequent transaction. All right? Unlocking transaction output. So that is about Bitcoin. Now, what is about generation 2? Generation 2 is the first technology which really allowed us to execute arbitrary Turing complete programs. So this is first Turing complete scripts, smart contracts. And that was in 2015. Not so long time ago, but now it is, you see, 2 generations behind the current state of the art. Which means that still the primary purpose of the Ethereum blockchain is to support transactions in the Ethereum cryptocurrency, ETH. Originally, if you remember, it was another one. It was ETC, what is now called Ethereum Classic. How Ethereum Classic turned into ETH, do you remember this story? A major vulnerability was discovered in the Ethereum blockchain itself, which was, by the way, related precisely to insecure execution of smart contracts. A major theft of funds occurred as a result, and in order to basically prevent the thieves from making use of the funds stolen, a decision was made to fork the Ethereum implementation so that legitimate nodes, the majority of nodes which were legitimate, they switched to the new implementation, which was not backward compatible, and those who had stolen the funds, they retained obviously the stolen crypto tokens, but the value of those tokens as a result of a fork significantly diminished. So the original currency, which was left behind after the fork, was what is now called Ethereum Classic, and the new one is Ethereum as ETH. So that was in 2016. It was one of the major vulnerabilities, not the only one, but one of the major vulnerabilities discovered in the Ethereum network, and there are some others since then. And I would say that in general, adding Turing complete smart contracts contributed a lot, and a lot to insecurity of the Ethereum blockchain. Most of those issues had been fixed since then, so now we can say that in the recent years, Ethereum is generally secure, but generally secure means there are no obvious vulnerabilities which manifested themselves. Whether we can prove that it is completely correct, then obviously we don't know. Because unlike in the chain, there is no proof for the formal correctness of Ethereum components. Moreover, as you know, basically implementation of Ethereum is not unique. There are multiple implementations. There are many programming languages in which you can find implementations of Ethereum nodes, and you can run as a node any of those implementations. It would still be a valid Ethereum node because it fully complies to the distributed protocol. It would accept blocks of data precisely in the same format as other nodes would accept. So it is completely standard practice that when a new blockchain technology is introduced, that multiple implementations of a particular technology would exist. In addition to multiple implementations of the node, there are multiple programming languages for Ethereum smart contracts. And probably the two most widely used ones are Solidity and more recently adopted Viper. But quite a lot actually of programming languages do exist. So for example, it is also possible to develop Ethereum smart contracts using JavaScript, Go, C++, Python, and so on. And all of them are translated into Ethereum virtual machine bytecode. And then executed on the Ethereum virtual machine, which is a part of each and every Ethereum node. Deployed, we have discussed it, but we'll repeat the point, and executed at every node. So I would say that Ethereum is a dual purpose distributed ledger technology. So yes, one of the primary objectives is still to support, as we said, to support transactions in Ethereum. Only these transactions can be of any complex type. It's not just uh, subtracting funds from one account and adding them to another account. There could be absolutely arbitrary conditions imposed on that, absolutely arbitrary programming logic, but in many cases, the ultimate purpose of this logic is still to manipulate some Ethereum accounts. Or Ethereum can be used as just a general purpose computing platform. So you would, even without the objective of transferring Ethereum between accounts, you would use it as a general purpose distributed database and a general purpose distributed computational network. Let's see. General purpose distributed database and distributed ledger system is, as we know, precisely distributed database. Or distributed computational platform. If computations are performed by multiple nodes of the Ethereum network, then the results of those computations are stored in the same distributed database in the Ethereum blockchain and made available to all other nodes on the network. So this makes Ethereum already quite interesting. We can probably take a step back and recall that distributed computing started became quite popular already in 1990s with the advent of internet, when internet connectivity became a matter of fact. If you remember, maybe you do not remember that period in 1990s, probably not. There was a number of infrastructures proposed at that time. So this was called grid computing. The term grid computing over the internet, it still exists. Can you recall possibly some maybe interesting, remarkable grid applications developed, let's say, for the past 20, 25 years? Have you seen any remarkable grid applications? What we mean by grid application is that there is a large heterogeneous network of computers on the internet connected to this grid. This could be either personal or research or any other computers which participate in some kind of distributed computations. And for distributed computations, typically we would use computationally hard algorithms which rely upon significant computing power available from those multiple, maybe hundred thousands and more nodes connected via grid infrastructure. So, any example of grid computations? Do you remember?
Previously, we mentioned sets at home by Berkeley.
Yes, one of them. It was SETI at home, but actually quite a few of them, and let's call it X at home. X could be, for example, indeed, search, what is SETI? Search for extraterrestrial intelligence. Then it could be some, for example, protein structure discovery. You know that there are so-called primary, secondary, ternary structures of protein molecules, and typically they are so complex and complexly bound that when you observe it, for example, you observe it from different sides using X-ray structural analysis, you see all this, you know, a very complex protein molecular image being observed from this side, this side, this side by X-ray X-ray diffraction analysis. But the question is, what is the linear sequence of atoms in this protein structure? So how can we, this is a so-called ternary or secondary structure, how can we linearize it? Because in fact it is just a single chain, but it is so complexly curved and interwaved that discovering the linear structure, so basically unwinding this into a linear structure, which is a primary structure. And this is, let's say, not even a secondary. Secondary differs with ternary basically by degree of complexity of how it is packed. So let's say this is a ternary structure, something like this. Having multiple images of this ternary structure, you are trying to reconstruct the primary structure, which is an extremely computationally intensive task, and that was one of these X at home applications. Then medical, there is such a term, medical drug discovery, synthesis of new medications, etc. Basically, such grid infrastructure still do exist. You can install whatever client. Sometimes it is in the form of a screensaver, so it would only activate itself at the time when you do not use your computer, and donate your computational cycles to the community, trying to solve some important scientific problem. By the way, do you know, and SETI at home, did it discover anything? Any artificial signals? It did. It did discover an artificial signal, which proved to be possibly more than one, an end-to-end verification of the whole framework. But it was, well, it was quite interesting, but although artificial, it was our spacecraft launched from Earth. One of them was Pioneer 10, which was launched in 1972, and it is well beyond the boundaries of the solar system at the moment, and still at the time when this discovery was made, it was transmitting a faint signal. Now it is completely dead, and this signal was detected and properly selected from the noise and identified and demonstrated that this SETI at home did work. There are, interestingly, there is a close parallel between grid computing and distributed ledger systems. So systems, for example, like SETI at home, this grid computing, is completely public. So this is a completely public one. But there are also corporate grid computing systems. They are not open to the public. These are just large computational clusters which are intended for high performance distributed computations in a corporate environment. So a very typical situation when it is indeed needed, this corporate grid, for example, data center wide or maybe more than data center wide, is in financial computing. I will explain why. Imagine an investment bank, and this investment bank has a sufficiently large portfolio of financial contracts. These financial contracts are typically derivatives, and these derivatives are quite complex, may be quite complex ones. So imagine, probably maybe you have heard about futures, options, other financial derivatives. Do you have any idea actually how it works?
Yes.
Okay. So for example, an option is a financial contract which allows its holder to receive, generally speaking, to receive some kind of payoff at the expiration of this contract, or maybe there are some option types which are called American options, which allow the holder to receive this payoff at any time if the payoff is positive. The problem is, in very many cases, the payoff would be zero, and the holder of this contract actually holds a kind of lottery ticket. They bought this financial contract, paying a premium upright, in the hope that at the expiration or any time prior to expiration, if allowed, this contract would deliver some value, some payoff to the holder. But very much like a lottery ticket may end up without any payment, right? Without any payoff. In a similar way, an option may end up without any payment to the holder as well. So an investment bank may have an overall portfolio. Imagine just, there are thousands of traders working for an investment bank. It is completely normal that for a large investment bank, for example, there are 1,000, maybe 2,000, maybe more traders. Let's say 2,000. And every day, a trader makes at least one trade in with counterparties from other banks, from counterparties in the industry, from with counterparties from the general public, makes a trade in those financial derivatives. And an option, as I described it, is only a very, very, very simple example of an option. There could be much more complex options. So, for example, the payoff is paid not only at the end point at the expiration of the contract, but it could be paid, for example, monthly, and the payoff depends on the number of dates a particular interest rate was above a particular threshold, something like that. So there could be a very, very, very complex set of financial securities, and there are many of them. So millions, and all those financial derivatives could be they do have some current value, and they do have risks associated with them. Because if, for example, you are a bank and you hold a short position in the option, so for example, you sold an option to someone, then you would be required to pay the payoff of that option. So there is a risk that the payoff appears to be large, and you would need to spend your capital on the payoff. There are multiple ways of how those instruments can be hedged to reduce, or sometimes maybe even completely eliminate, although it doesn't happen to completely eliminate, the risks for an investment bank. So what it means is that for those millions of instruments, you typically need on a daily basis compute the value of your portfolio and you need to compute the portfolio risks. By risk, we understand something which is totally and completely unpredictable. However hard we try, we cannot with certainty predict, for example, where the prices of this or that stock, or this or that currency exchange rate or interest rate would move. And therefore, there is always a remaining uncertainty about the future value of your portfolio. And this uncertainty, its probabilistic distribution is considered to be a risk. There are many measures of risk. I'm not going, obviously, to discuss them now, but it is extremely important to have them at least quantified. If you don't know where the value of your portfolio with certainty would go to, no one can say, then at least you know more or less what is the typical magnitude of this movement. So, for example, the value at risk of your portfolio is about 1%. Then you at least know, or more or less, what kind of risk exposure you have. And for millions of instruments, valuing the portfolio and the risk of your financial instruments becomes quite a complex task. Because imagine that the value and risks are typically computed using some kind of either Monte Carlo methods or solving partial differential equations. It's difficult to say how much computational time it would take, but let's say on average for a complex instrument, even if it takes, and that is a very, 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 I would say, optimistic estimate, if 1 second per instrument, and you have 1 million of them, and 1 second is typically a very, very optimistic value, then it is already 10 to 6 seconds per CPU obviously, which is for one CPU. What is 1 million seconds? 1 million seconds is about 11 or 12 days. All right. Um, because you typically need these results to be available within a few hours, then okay, if it is 1 second per instrument, then your computational grid doesn't need to be that large. So basically, 10 or slightly more than 10 high performance CPUs would be sufficient for that. But there are very complex instruments, in which case it is not 1 second, but it could be 1 minute and sometimes even maybe up to 1 hour per instrument. And there are millions of instruments. So you do need, in this case, thousands and hundreds of your high performance CPUs in order to be able to evaluate your portfolio on time. So typically, this is done by constructing a corporate grid hosted in some data center with the remote administration facilities, and computations are carried out of this grid. Let us probably discuss from the architectural standpoint, what do you think, what is the principal difference between grid computing and distributed ledger systems? Because we do know that we may have non-public, for example, private or corporate, distributed ledger systems as well. For example, third generation of distributed ledger systems, in particular, Hyperledger family of technologies, it is precisely intended for construction of typically, not necessarily, but typically private corporate size distributed ledger systems. So what is the difference, for example, between maintaining a corporate distributed ledger system and a corporate grid? What do you think? Any ideas?
I think that generally when people say grid, they mean something heterogeneous. Means
Not necessarily. Not necessarily. In this grid environment, you mean heterogeneous or homogeneous?
heterogeneous.
Heterogeneous. Okay, heterogeneous. Yes, true. I would agree with that. Yes.
And on the other hand, ledgers, they would be something like homogeneous. All the machines will be equal in some sense.
Ledgers, you mean homogeneous from the point of view of the hardware used or of the state?
I'm not sure. It's just a guess.
You see, from the point of view of let's say your hardware nodes, then definitely not homogeneous. None of them is homogeneous, actually. Because in any case, there could be absolutely arbitrary types of CPU, both maybe Intel and ARM and others, and same SETI at home and Ethereum nodes, for example, they can run on a large number of different operating systems, different hardware platforms. So both of them, I would say, would in general be heterogeneous. From the state management point of view, there is a big difference, and that's what we should point out here probably. So in a grid infrastructure, typical architecture is that there is a certain, maybe more than one, but let's say there is a central controlling node which sends tasks to be processed to grid nodes, and a grid node, when a task is complete, is sending the results back to the central node. So grids are typically centralized, and that's a very important thing. So the general state is accumulated by one or more, but still some dedicated centers of the computational grid, which get the results back from the working nodes. So these are working nodes. This is the admin node, which performs distribution of the workflow. Admin node or nodes in plural. Okay, whereas the topology of a distributed ledger system is quite dissimilar to the topology of a grid. And in that case, as you know, the state, so in case of a grid, the current state of the computation is accumulated at the admin node. The working nodes only perform their own particular partial computations, but they never have a full view of the system. So if you run SETI at home, then you do not, your node doesn't really know whether, a signal from extraterrestrial intelligence has been discovered or not. You're only given some computational tasks and you return the result. What in digital signal processing, what is in general happening, and how many aliens have been discovered so far, your working node doesn't have any idea of. Whereas, contrary to that, distributed ledger is completely symmetric. So all nodes exchange information with all other nodes, making a fully connected graph of communications. And a consensus algorithm is run across all nodes. All nodes are equal. There are no admin and working nodes. All of them perform similar computations, and then they perform, according to the consensus protocol, message exchange in order to equalize, as far as possible, to equalize the state between those nodes. So that's the principal difference. You may have heard about other similar technologies. What about, for example, MPI? Have you heard about MPI? MPI simply stands for Message Passing Interface. Have you seen it? It was developed, I would say, nearly 30 years ago, and still very popular, for high performance numerical computations. Well, similar to grid computations, actually. And this is like for solving problems like computing in inverse of a very, very, very large matrix, solving large systems of linear equations, performing integration of large systems of ordinary or partial differential equations, something like this. The standard paradigm which MPI follows is a single program multiple data SPMD paradigm. And from that point of view, you can think that if it is a single program, multiple data, it means that identical computations are being performed on multiple data items, that it is somehow close to a distributed ledger, but in fact it is not. Although single program, multiple data, there is still a controlling node which then accumulates the results. So basically, MPI is much more close to the grid paradigm than to distributed ledger. Because there is of those single program, there is still one which is not exactly single, which accumulate the results coming from others. And unlike grid, MPI is typically for local area networks, not for the internet. You can run MPI on the internet, but it is typically for the tasks where the cost of communications is not that prohibitive. So unlike grid, MPI is for much more intensive communication between the nodes, and the cost of communications is in that case comparable to the cost of computations. For a grid, it is not the same. So a grid, for example, sends a large computational task to your computer. The amount of data is relatively small, but the computational resource required to process that data is large. Then your computer spends, for example, 1 hour in a screensaver mode to perform a computation, and then sends a very, very brief result back to the admin node, basically yes or no. Any kind of signal has been discovered or has not been discovered in this computation. So basically, MPI is centralized computation for local area networks and dedicated hardware. There are systems like InfiniBand, which are very popular with MPI computations. Have you heard about InfiniBand, by the way? What is it? No? Any idea? Okay. I think it is worth mentioning at least. So we do know what we compare our technologies with. Okay, if you have Ethernet, just the classical Ethernet, not Ethereum, but Ethernet, what kind of speed do we typically have for Ethernet communications? You plug Ethernet cable into your computer, and what kind of data exchange throughput do you have over Ethernet?
I think there are some broadcast messages addressed to the main switch or something just to get the IP address inside the network.
I'm not talking about the technology, I'm talking about the speed, about the data throughput. So how fast are typically your Ethernet communications? How much data in, let's say, megabytes or gigabytes per second can you send over the standard Ethernet? Well, the very common standard nowadays is 1 gigabit per second. There are faster implementations. So, for example, fast Ethernet. And this is the standard if you do it using just the standard RJ45 connector and category 5E or 6 cable. Then with the standard hardware nowadays, you would normally have 1 gigabit per second speed. The previous standard was 100 megabit per second, which is still used sometimes somewhere. The very first one was 10 megabit per second, but that was a long time ago. So now 1 gigabit per second is completely standard. And that's why your home internet communication is typically, the speed is typically limited by the speed of Ethernet communications. In Innopolis, the maximum you can get is half a gigabit per second, for example. Fast Ethernet, which uses typically either optical or high quality electric transceivers, but it is nowadays also quite common, is 10 gigabit per second. There are even faster, maybe up to 40 gigabit per second, which is already quite a lot. And InfiniBand is a technology built upon fast Ethernet. Basically, these communications for InfiniBand, what is the range, for example, for this Ethernet communication at that speed, for example, 10, let's say 1 gigabit per second. 1 gigabit per second, you can get up to maybe 100 meters. 10 gigabit per second may be up to, let's say, 10 meters, and so on. So I would say it is a range of 10 meters. InfiniBand, by using high quality transceivers and cables and switches and so on, it can achieve 56 and so on up to 400 currently, maybe even more. But 400 is already well-established value, gigabit per second transmission speeds. And 400 gigabit per second is already the speed comparable with the front side bus speed at which your CPU communicates with the memory. Because if your memory speed is depends, but suppose that your memory clock frequency is, let's say, 3 gigahertz for the RAM, and in 64-bit systems, 3 gigahertz needs to be multiplied by 8 bytes. So then a single interchange would be 8 bytes. Then it is 24 gigabyte. Gigabyte per second, all right? And roughly I multiply by 10 rather than 8, just for the sake of the argument, it is 240 gigabit per second, because in Ethernet 1 bit is 1 byte is 10 bits actually. There are also some control bits used. So basically what it means that the high speed InfiniBand provides communication speeds which run at the same speed as your memory data exchange, and even faster. It is still less, the speed is lower than that of CPU to L1, L2 cache communications, but it is same speed as CPU to RAM interchange. So what does it mean? It means that by using InfiniBand, you can connect several computers together, typically within one cabinet in a data center, and you would get transparent communication between the memory of them. So basically, this is memory to memory or single memory pool type of communications between them. And this is a reality. Instead of just partitioning your computation, you can pretend that your computer system has just multiple CPUs, as many as in this cluster, and a single shared memory, and structure your computation that way. And that's what MPI, especially good implementations of MPI, typically make use of. MPI library, they typically have special interfaces to InfiniBand drivers, and that way you can build, I would say, a reasonably fast supercomputer out of commodity of the shelf hardware and InfiniBand interconnects. But that's local area. So all this, just a range of computation is a few meters. On the other hand, distributed ledgers are, first of all, completely distributed over the internet, are heterogeneous, and they are much less completely decentralized. Fully distributed over internet, or internet maybe if corporate. Yes, heterogeneous, and most importantly, no single point of control or admin node. Okay. And also, as follows from the previous point, is that computation results, we're not talking about financial transactions alone. We're talking about general computation results. In particular, yes, those computation results could be funds transfer in a corresponding cryptocurrency, but it could be a general purpose computations as well. Computation results distributed, not only computations, but computation results are distributed over all nodes. So my question is, what do you think? Could it be possible to run CT at home over the Ethereum network, for example, over the distributed ledger, which is the Ethereum blockchain? Can we implement a smart contract which runs any of those computational intensive tasks, like SETI at home? Computationally, is it possible?
Why not?
The answer is, of course, yes, you are right. SETI at home over Ethereum. Yes, it is possible. Let us even think what kind of architecture it could be. It does need external inputs. So, for example, those raw recordings which come from radio astronomy observatories, which we then examine for any signs of artificial signals. Yes, so data inputs in blockchain systems are called oracles, if you know. Data inputs, oracles, not to be mixed up with the Oracle database management system, of course. Receive radio astronomy data. Computations on all nodes. Distribution of results. What do you think are advantages and disadvantages, let's discuss that, of implementing SETI at home over Ethereum? Because if we now in our discussion we decide that some advantages do exist, then we may in our project this term do precisely like that. So do some complex digital signal processing, maybe a kind of SETI at home over, for example, Ethereum. But still, do you think it is a good idea? What are pros and cons? There is one pro. Ethereum network is very large. So basically you have quite a lot of computational resources. But what are the cons? The negative side, the downside.
All nodes are computing the same values.
First of all, yes. So all nodes are computing same values. Well, this is not exactly the case, because this would be the case actually if we are not allowed to have any extra inputs, any randomness, for example, in our smart contract implementation. But in fact, we may have this randomness, and it is possible to create a situation in which different nodes compute actually different, take different computational paths, but the results of these computations are then exchanged between all nodes. So in general, we can do that. Although it is not what distributed ledger systems are intended for. So you can partition your computation over distributed ledger, assign labels to those partitions, and then exchange your partitioned computational results over the whole network. So possible, but not the ideal way of how your distributed ledger system could be used for that. So can be mitigated, but ugly, I would say. That's one point. Another point, and a very important one, is that computations in the Ethereum network do not occur for free. It is not free. Execution of any smart contract has a cost. Do you remember how this cost is measured and what do we have actually to pay for this cost?
Gas.
Gas, of course. So Ethereum computations use gas. Gas is a special kind of crypto token used by the Ethereum network. All computations, you remember how is it? How is it done? All computations have a fixed cost in terms of gas. So all Ethereum virtual machine instructions, and obviously when the virtual machine works, it counts the number of instructions executed. So all virtual machine instructions have fixed cost in gas. The cost in gas is fixed, but the cost in Ethereum is variable. And transactions offer variable gas to Ethereum exchange rates. And then you remember what happens. All the transactions, because it is a public network, all the transactions are secured by the proof of work algorithm, right? And the miners would, of course, select for, as a first priority, those transactions which offer larger gas to Ethereum exchange rate. So if you put this exchange rate at 0, you can do that. And you are trying that way to execute your smart contract code for free, then maybe eventually at some point, sooner or later, maybe you would get it. But you would need to wait long time before some miner would probably pick it up and you would get your transaction executed. The higher gas to Ethereum exchange rate you offer, the more likely your transaction is to go ahead, if you remember. So you need to pay for that. Whereas running Ceti at home is completely free because those people who agreed to run it on their own computer, they did it just probably as a sign of support to the science, and they freely donate their CPU time at the time when it is not required and your computer is running a screensaver for CT computations. Okay. Another disadvantage. What is another con of doing this over Ethereum? Although the pro, just having a large computational resource, is a significant one, and you know what? Not only large, but it is fully publicly open. So you don't need anyone's permission, for example, to install this software on their machine. You don't need to ask people to install any client. You go for those general purpose Ethereum nodes and you submit a smart contract. So if someone runs, and that is a very important point actually, if someone runs a full Ethereum node, then an Ethereum node is prepared to accept any type of smart contracts which is submitted to the network. So, for example, you can't say, if you run an Ethereum node, you can't say, okay, I like this contract, I will run it. I don't like this contract, I will not run it. You will run transactions pertinent to all deployed smart contracts, all right? So that's a big advantage. But the disadvantage is that they need to run on a virtual machine. A virtual machine run code is usually by all means significantly less efficient than the code run on the CPU. The machine instructions run directly on the CPU. So there are significant efficiency issues here. Apart from Ethereum virtual machine, what are other virtual machines you know? Where there are virtual machines? I mean, virtual machines which run architecture neutral, synthetic, artificial bytecode. Let's recall. Which virtual machines do we know?
Java.
Java.
Of course, the best well-known is the Java virtual machine. Apart from that, what about Python? Python is also a kind of virtual machine. It is an interpreter of bytecode. When you compile your Python file, py, then you create either pyc or pyo. C is unoptimized, O is optimized, and this is a bytecode. Then the Python interpreter simply interprets the bytecode. So in effect, it is a virtual machine. Although we don't call it a Python virtual machine, but it is. Any other bytecode interpreters, for example, Erlang?
V8 for the JavaScript.
For the JavaScript, how is it called, you say?
V8, it's Google's version of it.
B8?
V.
P8?
V.
B for brother?
No, V for Vendetta.
Oh, okay, V8. V8, like that.
Yeah.
Okay. To be honest, I haven't done anything with Java script, so I didn't know about that. Thank you. Bytecode for the OCaml language, WebAssembly, and so on. So all major, well, .NET and .NET Core, ETP, and that almost all modern computational technologies are somehow related to virtual machines. There are very few, and the notable exception is, for example, C++, which is compiled directly into machine code and run at full native speed. A vast majority of others is compiled into bytecode and run on a certain kind of virtual machine. So what can we say about the efficiency of those virtual machines? Suppose that native code is 100%. So what can we say about the efficiency of, let's say, Java virtual machine compared to that? What's the idea?
It really depends on the way, like, in what you do, because the JVM is heavily optimized for on the way optimizations. I mean, it uses hot paths which are not really available with the compilation time, but they are available at runtime, so can be even faster than the native code.
Well, typically not faster than the native code, but I would say up to 70% of native code. It is reasonably good. Again, it depends on what you are doing. For example, if your computation is well localized, it could be as fast as that. If you create a lot of objects and do a lot of memory management, then it is significantly less, but it is something like that. That's true. Okay, so please wait a second. I will need to reconnect a power supply for my computer, and I will get back to you in a minute. Okay, we're back online. Whereas other virtual machines are much less efficient. So for example, considering Python and Erlang virtual machines, they would give you, let's say, 1 to 3% compared to the native speed. So dozens of times less efficient than the native code. Whereas Ethereum virtual machine here, I don't exactly know, but I would get that it is toward the lower end of this hierarchy. So it is definitely not as fast as Java virtual machine. For this reason, this would simply be hugely computationally inefficient. Although third generation blockchain technologies or distributed ledger technologies, for example, for Hyperledger, we have a high degree of optimization, and there are programming languages like Java itself, JavaScript, and even Go, which is typically quite an efficient implementation, which allows you to create smart contracts for Hyperledger. So having seen all that, let us lay out the objectives of what we are going to do in this course. So first of all, there was a choice between our fourth generation system in the chain is unfortunately still under development. So it is not quite exactly ready for smart contracts development in our educational model yet. Although first smart contracts have been developed for in the chain already, and even more importantly, have been verified. So that's a very important development. What can we do for our purposes to have an idea of how to program smart contracts? We could use either third generation or we could use Ethereum. Both have pros and cons. A high-end and a major industrial impact would probably be with Hyperledger. But in that case, we would need to take all this trouble. First of all, Hyperledger is not a ready-to-use infrastructure. It is a framework. If you remember, for example, for Hyperledger Fabric, there is a pluggable consensus protocol. So it is a kind of Lego framework from which you can build your own distributed ledger system, but it is not something which is ready to use out of box. So if we were to concentrate on Hyperledger, then our course would be probably a different one. It's not about, would not be about smart contracts programming, but it would be about do it yourself distributed ledger system. This is a little bit too much. That's not what we are prepared to do now. What we would like to do is to rely upon an existing well-established infrastructure to which you can very easily connect with lots of nodes already available. So you don't need to think about implementing your own Lego type distributed ledger system, plugging in the consensus protocols and so on, and then developing smart contracts, deploying it, administering it, and then developing smart contracts for it. What we really want to do is just to develop smart contracts, given the scope of this course. And for that reason, I decided that we would be much better off concentrating on Ethereum. So I would like to ask you, are you okay with that? So, or you really want to see, to have our course based on third generation? I think that using Ethereum is perfectly okay. It will teach us a lot. It will allow us to do interesting, meaningful tasks without paying any costs of developing and deploying the infrastructure by ourselves, which would more distract us rather than doing a good experience. What do you think? For that reason, we, at least, my decision, unless there are strong objections, my decision was to base our course on Ethereum. Any objections to that? Probably not. And then the plan is, first of all, as you know, Ethereum was created for financial type transactions, not necessarily in ETH currency, but for being able to create new coins. A coin is a smart contract which adheres to some special APIs or standards. Basically, what are these standards for? These standards are for standard operations with those coins. And what are standard operations with those coins? Transfer of them from one account to another, using them as a collateral for probably other coins, requesting those coins through ICO mechanisms, and so on. So coins are for financial type transactions. And there are even Ethereum standards for coin API. So if you develop a coin, it is a smart contract which must allow us to perform standard types of transactions with them. And you already remember possibly how these standards are called. ERC20, the classical one, and still by far the most popular one. What the next? Do you remember? ERC71, right? And the most recent one, you remember? 1155. So our first task, well, zeroth task would be to examine those standards, to see what they mean, and to select a standard which would be suitable for implementation of our coin. It would be nice to call it InnoCoin, but InnoCoin already exists, so we would use another name for it. So we would create a new coin. And then fully implementing a standard. We'll test transactions for this new coin. And after this new coin is created, the second task, I really hope that we'll have enough time for that, would be a much more challenging and much more interesting one. That would be to construct a distributed exchange, not a centralized exchange, but a distributed exchange, which is or called DEX. DEX is a distributed exchange, which is implemented by itself as a smart contract and would allow people to submit limit orders and maybe market orders, allowing them to exchange, if they want, of course, this our new coin for Ethereum. Obviously, it is a toy example. I'm not really sure that our new coin would be of any economic value unless we back this new coin by something economically valuable. If you create a simple coin, it would have a zero value. People start paying money for the new coin, even there is an economic value associated with that. There is an economic value associated with Ethereum because Ethereum can be exchanged to real fiat currencies, like, for example, USD. Many other coins do have some kind of value. There are even, no doubt you have heard about that, there are crypto dollars, which are crypto coins, which stand for United States dollar, and they have a value roughly, typically plus minus 1%, the same as the value of USD. Can you, by the way, name of USD like stable coins, so-called stable coins?
One of them is DAI. DAI.
DAI. To be honest, I haven't heard about it. Okay. But by far the most important one is USDT or Tether. And another one is USDC. Both of them stand for USD. Only USDT is implemented on actually both Omni blockchain and Ethereum, and USDC is on Ethereum itself. What, for example, Tether does? They claim, and to some extent, even the auditing which was performed with this company by external auditors, it to a large extent supports this claim that they receive dollars put from those who would like to exchange those dollars for USDT. They take those dollars out of circulation, so they put it on the bank account of the Tether Corporation. And for the amount of dollars received, those dollars are now dead for the economy because they stay put without any movement on the company account. They issue the corresponding number, create the corresponding number of USDT tokens. For this reason, the number of USDT, the total value of USDT tokens should be equal to the total value of dollars they support. And in general, it is like that. So the value of USDT to USD is really very close to 1, and sometimes even actually USDT is typically even slightly more expensive than USD. USDT costs about $1.01, something like that. Why do you think USDT could be more expensive than the dollar, more valuable than the dollar? What is better about USDT compared to the dollar? A free circulation. In order to make a transaction in USDT, you just need to create a wallet and to connect to any exchange, or even to connect directly to the Ethereum network, and you would be able to do a transaction. Extremely simple. If, for example, you receive USDT from someone in the United States, or the way around, you pay USDT to someone abroad, that is extremely easy. You don't need a bank, you don't need any intermediary, you just need access to the internet, and then you connect to the Ethereum or Omni network, and you do a USDT transaction or USDC transaction. So it is great. These are dollars completely like cash, completely outside of any banking technology regulation, fees, oversight. You do with them whatever you want, like transacting cash, with the extra advantage that you can instantaneously send this cash to any other country. So for that reason, USDT and USDC are great things.
But at the same time, you need to have a history for all these law enforcement agencies where you got this money from, and for that you will pay some kind of commission for laundry people, and it can be even more.
So what do you think? Law enforcement agencies, are they monitoring USDT transactions or not?
No, they can, like, of course they're monitoring them, but maybe not on that scale. But what I'm saying, if you would like to, let's say, buy Lamborghini in Russia, you will be immediately asked where you got this 20 million rubles from.
Of course. And if you buy a Lamborghini in USDT, which you probably can, then no one would ask anything.
In Russia.
Anywhere. Unlikely. Unlikely to ask. Unless you are under surveillance on your own. So they're already watching you. So it is really, well, let's put it in diplomatic terms, less regulation, more transparency, and I would say much faster transfer speeds. So in about an hour or less than that, any amount of USDT or USDC would be in any part of the world after a suitable number of network confirmations. You remember how transactions in Ethereum, for example, work. And by the way, Omni is just a clone of, if I remember correctly, it is a clone of Bitcoin blockchain, but not Bitcoin itself, because Bitcoin blockchain itself only runs the Bitcoin, currency. There have also been many clones of the Ethereum. So not only just the official Ethereum network, but many clones, which, because it is open source software, which people just clone by changing the names and some definitions and port address and so on, and created new networks that way. So the distributed, and another question is, can we really be sure that Tether really issued, because they are free to issue, a really same quantity of USDT as the quantity of US dollar they received? What if, for example, they made about 2 times more USDTs compared to US dollars? The auditors which examined at that time the Tether accounts, so the total value of USDT at that time was about 3 billion. They found about 3 billion assets altogether, but the structure of these assets was quite complex. So it was not just a single bank account with 3 billion. They were distributed across multiple bank accounts, also invested into other financial assets and so on. But if the auditors tried hard, they could find out about that much USD in the value of Tether as USDT created. But typically, it is completely a normal banking practice is to issue a larger number of banknotes compared to the number of deposits received. So a bank could make a credit emission with the amount significantly larger than the total deposits, in particular deposits in, let's say, hard currency or gold or any other completely liquid assets. Sometimes 10 or more times larger amount. And as long as there is a trust in those banknotes, then it is quite okay that the amount of credit and the amount of debit are I would say active or passive balance, it is more correct to say, would be different. So it may very well be that same applies to USDT, so that in fact a greater number of USDTs were created than the amount of USDs received. Some coins are not USDTs. A very well-known Russian TV star and singer Olga Buzova. You probably know her, although I have never seen even her, only heard her name. She created on the Ethereum platform, she created a coin which was precisely called Buz coin. And Buz coin was supposed to be supported not by USDs, but by free tickets to her concerts. But currently, if you check, by the way, the Ethereum network analyzer, Buz coin smart contract does exist, but the value of Buz coin is currently absolute zero. So it is not trading. We will create our own coin and a distributed exchange, which will allow us to make at least some real, small scale, but real transactions between our coin with the name to be invented. I did have a name, but I have forgotten it, and real Ethereum. So basically, our task for this remaining part of the semester is twofold. Identify a standard RC27211155 and develop a coin, and develop a distributed, simple but still fully functional distributed exchange, which would allow people to submit exchange requests for that coin. That's what we're going to do. Okay? That's all for today. Any questions, please?
Will we create a project like just one chain and like one coin and one exchange, or it will be just separate groups? Or
one coin and one exchange to provide operations for that coin. So once we get a coin, we will build an exchange. It will allow us to convert this coin into Ethereum.
So like 15 or how many of us will be working on one thing?
You mean how the team is to be structured? I propose a compromise in that case, that you split into a number of teams. So for example, a team of 3, team of 4, something like that. So if there are, for example, you say 15 students, then we can have 3 to 5 teams, and each team would work on their own implementation. And then the coins would also be different, obviously. Just coin name and the team number, or the team would invent their own name for the coin, something like that. Also, your implementation technology is up to you. Most people still find Solidity most useful, even to such an extent that Solidity very well captures the nature of smart contract programming. And that's why in many cases, even in our development of InnoChain, when the functionality of our smart contract was not yet completely clear, we first wrote a prototype in Solidity and then implementation in our supported programming language, which is KML, because Solidity is very good in thinking about the properties of smart contracts and capturing those properties. But if you have other preferences, if, for example, you would like to do it in Viper instead of Solidity, any team has absolute freedom in doing that. So please team up with your classmates, create the teams. You can put in our Telegram network, in our Telegram group, the name and composition of your teams. And next time we'll start examining the CRC standards.
Yeah, thank you.
Sorry, what is your task? Because we have some task on the lab right now, because lab is like
Yes.
started 20 minutes ago.
Yes.
There was presented some task about creating some coin. It is the same, or
It
what?
is the same, yes, it is the same. So
Okay.
for the moment, I think the first thing we need to do is to familiarize ourselves with the APIs of the coins. But the first task would really be about creation of the coin. In more detail, on Thursday, we'll discuss those coin standards. By the way, if for whatever reason, unfortunately, it may happen, you find some mismatch between our lab tasks and what we do in the lectures and so on, please immediately let me know, because all this can be adjusted and we can get them back in sync. What is the deadline for your current task? For lab? What is the deadline?
I think some of us did not attend the lab yet because we were here.
So we don't know.
Yeah.
Okay. So let's continue, if necessary, our discussion over the Telegram channel. So I wouldn't like to delay you any further.
Okay, thank you.
Okay. Please feel free to ask questions. Thanks. Thank
Bye.
you. Thank you. Bye for today.
Bye.
Thanks. Bye.
Bye.